Good day. This is one of two videos on chapter 6.3. In this video, we will extend polar coordinates to 3 dimensions. And there are 2 ways of doing it. In this video, we will be focusing on cylindrical coordinates. This is useful in evaluating special triple integrals. And this is also a special case of the transformation theorem for triple integrals. So, what is cylindrical coordinates? Now remember, normally when we are playing in 3D, we play with rectangular coordinates. So every vector has a 3D vector where the first component is x, second component is y, and third component is z, using rectangular coordinates. But in this video, we will be using cylindrical coordinates. So for cylindrical coordinates, you still have a 3D vector, but the first component is r, the second component is theta, and the last component is z. So how do you transform from rectangular to cylindrical coordinates? The diagram here is quite useful. So if you project point x to the xy plane, then you see that point P turns into point P dash. Now if you measure the distance from O to P dash, which is a projection of point P to the xy plane, that will be r. And if you measure the angle from the positive x-axis anti-clockwise, you will get angle theta. So this is the cylindrical coordinates. You take value r, you take theta, and you take z. So as always, this means that x is r cos theta, y is r sin theta, and r squared is x squared plus y squared, where r is greater or equal to 0. So this is the definition of cylindrical coordinates. Alrighty, so you got to know how to jump between rectangular coordinates and cylindrical coordinates and vice versa. So let's do an exercise where we jump from rectangular coordinates to cylindrical coordinates. This is example 17a. So we want to find the cylindrical coordinates for the point root 3, 1, 3, where we want the angle to be between 0 and 2 pi. Now, as you notice, to jump from rectangular to cylindrical coordinates, the z value doesn't change. So the tricky part is to work out the r and the theta. Now, it is very important to draw. So if you project that point to the xy plane, and if you forget the z value, then it becomes the following point. It becomes the point whose x value is root 3 and whose y value is 1. So you end up getting this point, root 3, 1. This is the origin. Let's call this point P dash. Now, r is the norm of the vector root 3, 1. And so, it is the square root of the first component squared plus the second component squared. So that's the square root of 4. And so the square root of 4 is 2, and that is positive, so we are happy. Now we've got to work out theta. Now guys, it's very important that you draw the point, alright? You can see it's in the first quadrant, so you know that theta is going to be positive. Now, tan theta is opposite, which is 1, over adjacent, which is 1 over root 3. So it's 1 over root 3. And so that means that theta is equal to arctan 1 over root 3. This is a special angle, and we don't need a calculator to work it out, and it works out to be pi over 6. Remember, it is in the first quadrant. And so now we can say that the point in cylindrical coordinates, I misspoke. Cylindrical coordinates is the r value is 2, the theta value is pi over 6, and the z value doesn't change, it is 3. So here is an example of moving from rectangular coordinates to cylindrical coordinates, alright? Please do example 179 to jump from cylindrical coordinates to rectangular coordinates. It's good to practice these things. Alright, so now because this is a transformation from R3 to R3, we can work out the Jacobian. And remember, the Jacobian will be, one way to notate the Jacobian R theta z would be partial symbol, the rectangular coordinates over the partial symbol, the cylindrical coordinates, which is the determinant of a 3 by 3 matrix. The first row would be x partial r, x partial theta, x partial z. The second row would be y partial r, y partial theta, y partial z. And the last row would be z partial r, z partial theta, z partial z. So if you work out the determinant of that 3 by 3 matrix and you simplify it, you get it to be r. So that is the Jacobian going from rectangular coordinates to cylindrical coordinates. And now we can formulate a version of the transformation theorem. So assume E is a subset of R3 and it's closed and bounded. And let F be a map from E to R which is continuous on E. And then we define F to be the image of set E under this transformation, i.e. F will be all the cylindrical coordinates of all of the points in set E. So that means that r theta z such that r cos theta, the x value, r sin theta, the y value, and z is an element of E. And this we want it to be a subset of the r values is greater or equal to 0. The theta values are from 0 to 2 pi, and the z values is any real number. Then it says the following, that the triple integral of f over E is equal to the triple integral of f over region F times the special factor, the Jacobian r dv. Alright, so the integral on the left is it using rectangular coordinates, and the integral on the right is using the cylindrical coordinates. So on the left you will have x, y, and z as your variables, and the one on the right you will have the variables r, theta, z. Alright, and you can see why it is an extension, because the Jacobian for polar coordinates is the same as the Jacobian for cylindrical coordinates, and they're both equal to r. Alright, now if you are lucky and the image of f can be written in cylindrical coordinates as follows, that the theta values are between alpha and beta, and the r values are between a function of theta. One function is r1 and the other function is r2, and the z value lies between two functions u1 and u2 of r and theta. Then we can say that the triple integral of f over region E can be written as an iterated integral of an integral from alpha to beta, an integral from r1 to r2, an integral from u1 to u2, where r1, r2, u1 and u2 are functions. R1, R2 in terms of theta, U1 and U2 in terms of R and theta, of the integrand times the special factor R, dz, dr, d theta. And so there's more comments on page 173, so please read those remarks on page 173. Alright, so this is how you jump from rectangular coordinates to cylindrical coordinates when working out a triple integral. So next we're going to do two examples to see this in action. Alright, so the first example is the following. Let E be the region in the above the xy plane, inside cylinder x squared plus y squared equal to 4, and below the cone where z is equal to 4 minus the square root of x squared plus y squared. You want to use cylindrical coordinates, so the Jacobian is r, to express a triple integral of 2z plus x over region E. Alright, so this one is quite easy to draw. You draw the cylinder x squared plus y squared equal to 4, and you sketch the cone z is equal to 4 minus the square root x squared plus y squared, whose maximum value is 4 when you're at the when x is 0 and y is 0. So it looks like the diagram on the left. Remember, you want all of the points above the xy plane. So this is solid E. And so we're going to do a triple integral over solid E. So we know what it looks like. And it's quite easy to see that you can describe E using rectangular coordinates. So you can say x, y, and z have to have the following properties. So you see that it's got to be inside the cylinder where x squared plus y squared equal to 4. So that means that x squared plus y squared is less or equal to 4. And the points have to be above the xy plane. So that means that z is got to be greater or equal to 0. And it's got to be below the cone. So z is less or equal to 4 minus the square root of x squared plus y squared. Alright. So from the problem description, we can see it is easy to write E in rectangular coordinates. Alright, now to express it using cylindrical coordinates, we care about the projection on the XY plane. So let's do the projection on the XY plane. Alright, so when you're doing triple integrals, you get practice into visualizing objects in R3. Here we can see if you project this onto the XY plane, it is quite easily a circle of radius 2 centered at the origin. So let's call the shadow D. And it's quite easy to describe D using polar coordinates. So we can say that R is between 0 and 2. It's a full circle, so theta is between 0 and 2 pi. So this is the projection of region E onto the XY plane. Now this is quite useful because this allows us to describe E using cylindrical coordinates. So now we can say it is all of the vectors R, theta, Z with the following property. Now R has got to be between 0 and 2. Theta's got to be between 0 and 2 pi. And now we've got to describe Z. Z is between 0 and... Now here is where you've got to think. Alright? If you are shooting a rocket, you can see it starts here when Z is equal to 0. And it ends when it hits this surface. When Z is equal to 4 minus the square root x squared plus y squared. So it starts there and it ends there. And now remember that x squared plus y squared is always r squared. And the square root of r squared, that's equal to r because r is greater or equal to 0. So we see that z ends when it's equal to 4 minus r. When you write this in terms of cylindrical coordinates, you only want to see r, theta, and z. You do not want to see x or y. So you only want to see r, theta, and z. So we've described E using rectangular coordinates, x, y, and z. And we've described E using cylindrical coordinates, so we only saw r, theta, and z. And now we are ready to write E as an iterated integral using cylindrical coordinates. So we can say the integral I is a triple integral. And now the integrand is 2z. So we keep the 2z. So z we keep. But x we got to rewrite as r cos theta. So the integrand must be in terms of r, theta, and z. We do not want to see x. We do not want to see y. So we replace x with r cos theta. Because we're moving to cylindrical coordinates, we've got to remember to write down the Jacobian. The Jacobian is r. And we're going to use the following order: dz, dr, d theta. So the angles are between 0 and 2 pi. It's a full circle. R is from 0 to 2. So that's the range of r. And z starts at 0. And z ends at 4 minus r. And that, ladies and gentlemen, is the triple integral written as a triple integral using cylindrical coordinates as an iterated integral with order dz, dr, d theta. All right, I'm going to leave it for you to do this calculation. If you do this calculation, you should get 88 pi over 3. If you get stuck, have a look at page 174. All right, so we've done an example. Let's do another example. This is example 183. So this time around, E is a region inside the cylinder x squared plus y squared equal to 2y. It is below the paraboloid z equal to 5 minus x squared minus y squared, and also above the xy plane. You need to express the volume as a triple integral using cylindrical coordinates. All right, so I've sketched the region E here on the left-hand side. So x-axis, y-axis, and z-axis. And this is what we have everything inside the cylinder, above the xy plane and below the paraboloid. Now again, it is quite easy to describe E using rectangular coordinates. So it is all the vectors x, y, z. So 3D vectors with coordinates x, y, z with the property that x squared plus y minus 1 squared is less or equal to 1. So here I completed the square. So please do that calculation. So completed the square to see that we want x squared plus y minus 1 squared less or equal to 1. And z is between 0 and 5 minus x squared minus y squared. So it's very easy to describe it using rectangular coordinates. All right. Now, we're going to use cylindrical coordinates. So again, we're going to look at the projection on the xy plane. So if you take region E and you project it onto the xy plane, you will see that it is a circle as before, but this time around it is a circle of radius 1, centered at the point 0, 1. So that will be 0, that value would be 2, that value would be 1, 1, this value would be minus 1, 1, and so this is the shadow or the projection on the xy plane. All right, so let's quickly describe D using polar coordinates. So we can see we only have angles in the first and the second quadrant. So theta this time around is between 0 and pi. So you see how it was useful to draw the circle, because now we can see theta is between 0 and pi, because we only have points in the first quadrant and the second quadrant. There are no points in the third and the fourth quadrant. All right. Now, if we draw a ray, you can see it starts at the origin and it ends on the circle. If I draw another ray, it starts at the origin and it ends on the circle. If I draw another ray, it starts at the origin and it ends on the circle. All right? So let's quickly do the calculation. So the equation of the circle is x squared plus y squared equal to, it is given as 2y. So x squared plus y squared, that's r squared. And remember, what is y? Y is r sine theta. So r sine theta. Now if r is positive, we get that r is 2 sine theta. So we see that region D is described when r is between 0 and 2 sine theta. All right. So when we project the solid onto the xy plane, we get a bunch of points where the angles are between ranges from 0 to pi and r ranges from 0 to 2 sine theta. So once you've picked an angle, we see that r ranges from 0 to 2 sine theta. And it makes sense, because if your angle is pi over 2, then r ranges from 0 to 2 sine pi over 2, which is r is between 0 and 2. All right, so here you can see you want the r values from 0 to 2. All right. Now we're happy because now we can describe E using cylindrical coordinates. So we're going to say r theta z with a property that theta's got to be between 0 and pi. It's in the first quadrant or the second quadrant. R is between 0 and 2 sine theta. And now we've got to say the z values. So when you shoot a rocket, you can see it starts here when z is equal to 0, and it ends here on the surface of z equals 5 minus x squared minus y squared. All right, so that means that z is 5 minus x squared plus y squared, which is z is 5 minus r squared. So you see that the z values ranges between 0 and 5 minus r squared. All right, so what we've done now is we have described E using cylindrical coordinates. All right, so now we're happy because now we can do the calculation of how to convert the volume using cylindrical coordinates. So we know that the volume is a triple integral over region E, and if you're doing volume as a triple integral, the integrand is 1 dV. All right, and now we continue, and so we're going to say this is an iterated integral. The integrand is 1, so it's 1. So it is in terms of r, theta, and z. And now, when we're moving to cylindrical coordinates, we've got to remember the Jacobian. And what is the Jacobian of cylindrical coordinates? Yes, it is r. And I'm going to use the following order. So I'm going to use the order dz, dr, d theta. Because first you pick an angle, and your angle is in the first quadrant or in the second quadrant. So the angle ranges from 0 to pi. Then R, we've already then established, ranges from 0 to 2 sine theta. And then Z ranges from 0 to 5 minus R squared. So you see we have this now as a triple integral, an iterated triple integral, and you only see the values theta, R, and Z. Alright, you only see three variables. It's a triple integral, so you only should see three variables, R, theta, and Z. Alright, so now I'm going to leave it to you to do this calculation. Alright, if you get stuck, the answer is on page 176. But if you do the calculation, you should get 7 pi over 2. I hope you've enjoyed this video. Please come back for the second part, which is a video on spherical coordinates. Have a good day. Bye.